I'm going to continue the set of lectures by thinking about the idea of optimal basis set and optimal basis selection. So, so this idea of optimal basis becomes really important for us, especially as I want to think about the idea of POD basis selection, or how to construct a POD basis, the proper orthogonal decomposition. So what we talked about last time is we were interested in solving some PDE of this form. And so we can discretize it, make it finite dimensional. And of course, we would like to solve this PDE in some way. And so by discretizing into some large n-dimensional system, what we had is a platform for solving a system of differential equations. So the idea was to say my U will now be a sum of some time-dependent coefficients times some basis elements. So that's what we're going to try to do. And the philosophy here has been that if I pick a nice basis set, psi of n, then I plug this in, I'm going to get a system of differential equations for the A of n, and I'm going to solve those by just time-stepping something like an OD45 scheme. Now, interestingly, there's this parameter n that sits up here. This is your dimension of your underlying ODE, and it turns out it depends a great deal upon the basis set you choose. Our goal is to say, if I discretize this into a very large high-dimensional system, I would like to do an expansion here where I can use the fewest number of bases and get some sufficiently accurate solution. That is going to be the goal of this exercise, is to figure out how do we do that. So the first step in this is to discretize this. And if n is the full high-dimensional system, so in other words, n is much bigger than 1, then what I'd like to do is say, well, I'm going to do a full simulation of the fifth system to begin with. This is going to be one of our assumptions we're going to have to make, at least in terms of selecting a basis set. And potentially I might select a Fourier basis just to start with, because without any pre-knowledge of the system, let's say a Fourier basis has spectral accuracy n log n speed, so I might just choose that as a standard way to solve things. But once I've solved this for a bit, I can start collecting my data into a snapshot matrix X. What X is the solution U, maybe at different times, U1, U2, all the way through U of M. So these are vectors. And these are just snapshots of that full system that I'm going to throw in there. So I've solved the full system. I have this high-dimensional vector space at time t1, t2, all the way to t of m. And I've used whatever method, whether it was a finite difference scheme or I used some kind of spectral element, or excuse me, spectral expansion, something like Fourier modes. And I've collected my data somehow. And it was costly. But now I stack it up. And so now what I'd like to do, because I was solving the full n-dimensional system, but the question is there some kind of low-rank structure I could take advantage of and pick out a really good POD basis set or an optimal basis set so that I can cut down my simulation time quite a bit because I have the right basis selected. So in selecting all those data and stacking them into my data matrix, I can now actually do our standard trick, which is to do a singular value decomposition on that data matrix. So now I'm going to decompose X into its singular value decomposition. And if you remember, we can always do a singular value decomposition, no matter what the data matrix X is. So there's my singular value decomposition of the data matrix. And here, let me just throw out some things. X itself is our data. So this data matrix is an element of complex numbers, which is size n by m. So I used here capital N. I'm going to switch it out to little n here. So little n is the number of rows. M is the number of columns. And presumably n is quite large. Now what this gives me are three matrices. U matrix, which is n by n. Sigma matrix here, which is actually, sorry, I'm mistaken in the notes. It's reals, that is n by m, and then v itself, which is m by m. Okay? So I get these matrices coming out of this, and you can look at the singular value decomposition lectures, and you'll see that I've talked a lot about what comes out of this. We've talked a lot about not only the full SVD, but the reduced SVD, and also things like economy SVD. And so what I really want to think about is this matrix U. When you do POD, you want to think about that matrix U that comes out. That matrix U contains the modes that dominate the correlative structure of the data matrix X. These are often called, if you're doing more general data science methods, these are your PCA components. Each column of the matrix U are your dominant modes. The first column is the most dominant, then the second most dominant, third most dominant. They're orthogonal to each other, and U comes out, they're orthonormal to each other as well. Okay, so an orthonormal set. So U itself is a unitary matrix, and what we want to do is take a small subset of the matrix U. In particular, the small subset that seems to be a nice indicator of capturing most of the variance in our data that we've collected. Well, how would I look at that? Well, typically what you would do is you'd also look at this matrix sigma. And if you look at the diagonal of that matrix, because it is a diagonal matrix, you're going to get some singular values. They're going to drop off. And of course, this is the ideal thing we'd like to see, is that there's a few dominant modes. Here I've drawn 4 or 5, and then the rest are kind of near 0. And what it tells you is that there are a certain number of modes that seem to capture all the variance or all the correlative structure in your data. And there's a lot of modes that don't do anything for you, which are all out here sitting on the tail. So this is going to be how we're going to start thinking about basis selection. We're going to select basis this U, but we're going to select them here and truncate and cut off at some point and say we're only going to take a small sample of modes, all the ones over on this side that have a certain amount of variance. In my introductory lecture, I talked about taking a small collection of the rows or columns of U, and I call these phi of R. So this is my rank R truncation. My first R columns of U are going to be called phi of R. So that's what we want to do in thinking about selecting optimal basis functions out of the system. And we want to start constructing all of our dynamics and all of everything we have in terms of these things. Now, I want to give a specific example, because this is all fine and good, but I want to solve a specific problem. In fact, I'm going to solve a linear problem. It's going to be the harmonic oscillator. And in this harmonic oscillator problem, we're going to go ahead and we're going to start looking at exactly these kind of metrics here. We're going to start solving, stacking our data, and then we're going to decide how many modes is it that we need to represent that solution effectively. And that will be our first example of sort of understanding how we might do this. But the harmonic oscillator also illustrates some other interesting points that we need to consider when thinking about doing simulation. So for instance, in this simulation here, if I take a snapshot of the data, the only things I can describe, or the only basis sets that can give me, are things that are actually observed in this simulation. So in other words, just because I get a POD basis set out of this, using the SVD, does not mean I can generically represent any solution of my PDE. I can only represent solutions out of my PDE that I've actually seen in my data matrix. I'm going to show you this to you directly in this example of the harmonic oscillator. And this is kind of why I like this example. It's simple to program, and it highlights for you some of the things we have to be aware of as we move forward in programming and using these architectures. Okay, so I guess I first should write down the equations for us. Here is the harmonic oscillator. It's a PDE. So it's got a Schrodinger type behavior. This is IUT. I is the complex imaginary number plus 1/2 UXX. So this is what's called the free space Schrodinger operator. Now Schrodinger was very clever. He knew that, de Broglie had already picked out the fact that, had already highlighted that there seemed to be wave-like nature in quantum mechanics. On the other hand, Heisenberg said that you cannot know the position and momentum of electron at the same time. So this was very interesting. So I need a wave equation, and typically a wave equation was UTT equals UXX. That was a standard wave equation at the time people thought about. It's a two-way waves equation. But that wave equation required two initial conditions which violated Heisenberg. So Schrodinger said, well, I need a wave equation, but I need to specify one initial condition. So this is the Schrodinger equation. Wave equation, one initial condition. So this is how this thing sort of was generated. And typically what you throw on here is some kind of potential. And for us, we're going to throw on this potential. And that is what's called the harmonic oscillator. It has a basically quadratic potential. Okay? So that's our governing partial differential equations, function of time and space. What we're going to do is we're going to go ahead and run this thing, and turns out this thing actually has an exact solution. And this exact solution are in terms of what are called Hermite polynomials, or Gauss-Hermite functions. In particular, the way people typically solve this is say, hey, look, what I'm going to do is I'm going to say that u is going to be some function of the form like this with a phase term like that. So if you plug this directly into here, what you end up finding is that you find an equation for the eigenfunctions psi of n. There it is. Now, interesting, this is in fact one of the special functions we talked about in the last lectures. This was discovered quite a long time ago, and this special function it's a Sturm-Liouville operator. And by the way, here the assumption is that this is quite a squeaky pen here, that the solution goes to 0 at plus or minus infinity. Okay, so this is one of the Sturm-Liouville form type solutions, and people knew quite a bit about it. And the solution to these are Hermite polynomials. So we have exact solutions to this problem. And what we'll do is we will actually compare our numerical approximation and our POD basis expansion to these exact eigenfunction solutions to this problem. Okay? So this is kind of the problem we want to consider. It's a classic of mathematical physics. Fairly simple. We're going to program it up and take us all of a few minutes to kind of get this code running and visualize some of the dynamics that it has. And then what we're going to start doing is saying, look, I'm going to take this philosophy of taking snapshots of the system and trying to see what, in fact, seem to be the optimal basis set representing the solutions. In particular, what does the SVD discover for us about this optimal basis set? And maybe we can even make connection to known exact solutions. Okay? So, in some sense, people were very interested in these special functions because they arose a lot in problems like this, which is, can you say something fundamental about physics because this harmonic oscillator was one of the canonical models to arise out of physics. And what partly makes a canonical model is the fact that, at least in this case, that you could actually solve it and write down an explicit exact solution. Okay? So let's go ahead and actually solve this thing computationally. And so we're going to go ahead and I'm going to pull back up MATLAB here. Come on, there we go. From our last time we were programming. And what I'm going to do is delete all this. Okay, we're going to start with a clean slate. And our goal here is to go ahead and start programming up this harmonic oscillator so we can look at the dynamics of that. All right, so first of all, we're going to define a domain to be on. Let's say L equals 30. And I'm going to chop this up into 512 points. Okay, so picked a domain. I'm going to chop it up, 512 points. I'm also going to go ahead and define my x variables. X2 is equal to a linear space that goes from negative L over 2 to L over 2 and n plus 1 points, and x is equal to the first 1 through n of those points. So I've got my domain chopped up. I've got my domain defined. Remember, this is the fact that it's periodic boundaries for the Fourier modes. I'm going to use Fourier mode expansion to solve this. So I've got this set up. I have to have my k wave numbers. K is equal to 2 times pi over L, and this goes from 0 to n over 2 minus 1, and minus n over 2, negative 1. And I'm going to make this transpose like this. So these are my wave numbers, and when you Fourier transform, one thing you have to remember is the Fourier transform does this shifting of your wave numbers, and so I shifted them back. Fourier transform also assumes you're working on a 2 pi periodic domain. Our domain is size L, so this 2 pi over L resets that. So the stuff we'll do here typically tends to be the stuff we cover in AMath 581. It's not so important that you take that. I mean, some of the steps you may miss in seeing this because we'll go a little too fast, maybe for that, but that's not really the point of this code. The point of this code is just to show you the dynamics and talk about this optimal basis selection. So I'm not going to worry too much about if you know all this in detail. You may or you may not. The point is, let's going to focus in at the end on optimal basis selection. Okay, so those are my wave numbers. So we're ready to kind of start solving this thing. So I'm going to give it some initial data. So let's do this. U is good. Let's just do a Gaussian. Okay, and my initial condition will be the Fourier transform of that. So the way we're going to solve this is we're going to take that equation I had written up here. We're going to solve it in the Fourier domain. Why are we going to solve it in the Fourier domain? Some very nice things happen in the Fourier domain. In particular, two derivatives of x, uxx. When you take the Fourier Fourier transform of something that has two derivatives, what it brings back to you is the Fourier transform of the function times ik squared. So it's one also very nice properties of Fourier transforms. It handles derivatives beautifully. The nth derivative, if you want to compute it with a Fourier transform, or you take the Fourier transform of the nth derivative of a function, is negative ik to the nth power times the Fourier transform of the function itself. It's a very clean result, and we can use that here. So we're going to solve everything in the Fourier domain by starting off with this initial data here. Okay? So what we do now is we call on, we're going to pull out the solution from OD45. So we're going to go ahead and we're going to throw it into OD45 to advance the solution. It's going to come out with the time and UT-sol. What UT-sol is, it's the solution in the transform domain. That's what I mean by UT-sol. So we're solving this in the Fourier domain, so what's going to come out is the solution in the Fourier domain, and then we're going to have to basically bring it back to the real domain. We also have to define a time to solve it for, so let's come up here and let's solve this thing for, I don't know, let's make t go from 0, steps 0.2 to 20. So we're going to solve it for 20 units in time. So when we call OD45, we basically call, let's call this harmonic right-hand side. It's going to call some function called harm underscore right-hand side. So it's for harmonic right-hand side dot m. It's going to go look for that file. That right-hand side is going to have our PDE encoding, so it's fine. We send in the time, the initial conditions. That spot is reserved for sending in things like tolerance settings. And we're also going to send in our wave numbers and our potential V. So with the wave number we've created, we still have to create V. So let's go create V. V we can create right here. V is equal to x squared. In fact, what we're going to do is do this, and we're going to send it in as a column. So there's our potential, x squared potential. That is a classic harmonic oscillator potential for Schrodinger. Okay? So we've defined our space and time, our wave numbers, our initial condition, and Fourier transformed it, and then we just call this function. Send all that in, let it compute, let it step forward in time, and solve this basically 512 degree of freedom system. Why 512 degree of freedom system? Because that's what I defined it. I said, look, there's 512 Fourier modes. And the nice thing here is that even if Fourier modes aren't the ideal basis set, which they clearly are not, I'll show you, they're fast, they're very accurate and they converge nicely, and they compute derivatives wonderfully. So the three things make them, so I pay the price of having a lot more modes, but it's very fast and accurate. And so maybe I don't have to think about optimal basis set. But what if this number instead of 512 is like 1 billion? Well, all of a sudden I have to start thinking about that. And this is actually the case of reduced order modeling, right? Is when you start solving extremely high dimensional systems, these numbers grow huge. And so what you need to figure out how to do is bring that number down by being really careful about your basis selection. Now before we go into the right-hand side, let's just talk about what's coming out of this thing. So what I'm going to do, I want to plot what I get out. So I'm going to go through, and for each t that comes out, so from 1 to length t, I'm going to try to grab this, get the solution now. Remember, the solution is in the Fourier domain, so I need to bring it back to the real domain. And so what I'm going to do is say, go grab UT-sol, go grab the jth row. Okay? That's what I want. And what I want to do with this is inverse Fourier transform it. So I go grab each row by row, and these are different time points. It's in the Fourier domain. I just inverse Fourier transform it. And I'm going to save this in a matrix. And this one's going to be called U-sol. So for the solution. That's it. Once I have that, I can plot u sol. In fact, let's just do it here. I'm going to do the following plot. I'm going to do a lit surface x, t, absolute value of u sol. Okay? So that's the outside. I'm going to run it, plot it. So now what we have to do is still create one other function, which is this harm right-hand side dot m. It's going to call that function. So let's open a new function here. All right, it's going to be a function, harm RHS. Okay? And I hope I printed it off, which I probably didn't. But we can very quickly derive it. So let's talk about this. It'll be a nice exercise. I wrote down this as the governing equation, minus x squared over 2 That was our governing equation. So what I'm going to do with this is I'm going to go ahead and take the I ut to the other side and multiply by I. So if I move it to the other side, it becomes a negative IUT. If I multiply it by I get a minus I squared, which is positive 1. Okay? So I get ut is equal to I over 2 uxx minus I x squared over 2u. Okay? So I have the ut where I want it, alone on the left-hand side of the equation. Okay? And so now what I want to do is Fourier transform everything. So the Fourier transform will be represented by a hat. So this is Fourier transform in x. So I Fourier transform, I get u hat t is equal to Fourier transform of two derivatives, pulls out an ikx squared. So I squared, so you get a minus I over 2 k squared u, and then here minus I, the Fourier transform of this term here, x squared times u. So there we go. This is our right-hand side right there. Okay? So that's kind of all you need to do to build this right-hand side from that equation. And, provided I didn't make any dumb mistakes here, then we could just program this in. And in fact, let's leave this up. This might work out to our advantage to have this. So the first thing I need here is to compute this term. I need back u. So I'd say, well, what comes into this is the time, as well as the initial conditions ut, as well as typically that third slot is for the tolerance settings. So I just call that a dummy setting. And what else did I send in? K and V. So I throw in K and V. So U is just simply IF to T UT. Okay, so that's the first step. Get U back. Now all I have to do is put this in and say by the way, my right-hand side that I'm sending back is equal to this. So my right-hand side I want to send back is the following. I want to say that it's minus I over 2 times what you have here, k squared times u hat, right? So k squared times ut. That's this term right here. Minus I over 2 times the Fourier transform of v times u. Remember, I sent in v. That was from the outside. We already computed it, so I sent it in times u. That's it. So there's our right-hand side. So we can save this. So we're going to go and save as harm.m, save, and then we can run this. Oop. Oh, linear space, not line space. Codes never work the first time you try them, usually. See if it works the second time. Looks like it's busy. And well, I probably shouldn't erase this because I might need it, but I'm going to go for it. Okay. Well, that's not good to write out to the screen. I'm missing a all right, it'll be done in a minute. So I forgot to put one of these here and one of those there. Okay, and mistype surf here. Surf, oh, okay. Let's try that again. All right, so now we're running this again. We'll see if we get the surf plot out, and then we're going to take a look at what we have in this. Okay? So this hopefully will run and give us a nice representation of the dynamics that might occur in this harmonic oscillator. And there we go. All right, great. There it is. So it's working. Check it out. Well, that's too big. No, I didn't want to do that. Okay, and let me go rotate this. That's that one. All right, so there you go. Oh, I need a shading interp in here. That's what's going on with this. And then we want this, and then shading interp. That'll make it a little bit nicer. And we'll just do that, so we just run that section. All right, there we go. So this is what this thing looks like. It's just an oscillating thing. So this thing is stuck in this potential well, which is a parabolic shape, and it's just simply doing this waveform. So simple result, really, out of this thing, but that's the dynamics of the oscillator. And I used 512 modes to get this representation. And the real question is, if this is the dynamics I saw, and I wanted to understand what are the ideal basis sets, how do I do that? Well, I can start applying the SVD directly to this data. Okay, so just keep this picture in mind, because when you look at it, it's a very simple structure, which makes you wonder, how many modes do I really need to represent what I'm seeing in this thing? Okay, probably not 512. So how many should I think about needing? So this is what we're after here, is we want to start thinking about this data matrix. And this data matrix, if you want to look here, size, if you saw, is 101 by 512. So the way it's currently stacked is time is the columns, the spatial the spatial stuff is in the columns and time is in the rows, and that's different than the way I had written it down. So what we're going to do is say my data matrix X is equal to, you saw, transpose. So now I have my data matrix, and you know what I'm going to do next with it? I'm going to compute the SVD of X econ. So that's going to take this thing, decompose it, and the first thing we want to look at, of course, is the singular values. So what we want to do is plot diag of S divided the sum diag of S, and plot those with big circles, line width, 2, and that should do it for us. Oh, let's see here. Something's not quite right. Sorry. All right. So let me just see what's going on here. Oh, I'm missing a parentheses. Sorry. Go back to that and run. All right. So this is a really important picture. Here's the dynamics. Clearly looks to be low dimensional, a very simple structure out of this thing. Here's what the SVD tells you. And with the SVD, in fact, what I've done I've set it up as the diag divided by the sum of diag. So what this is really the percent. So the first mode has about 68% of the energy, second mode about 20%. This one has about 8%. And you can see there's sort of essentially 4 or 5 modes that matter. Remember, I had picked 512 Fourier modes. And now what it says is that, well, actually 5 modes seem to matter. So I can potentially reduce my computational cost by switching to these modes and reduce it by 2 orders of magnitude in this example. Now the reason I only have 101 Fourier singular values is because in time I only sampled 101 times. Okay? Now let's take a look at what these things are, because that becomes very important. In figure 3, what we're going to do is plot the modes. In particular, we're going to plot the first column of U. In fact, let's plot the first 3 columns of U. Oops. Remember, this is complex data. So when we solve that equation, this had imaginary numbers in it. So I want to look at the complex values that are there. And here they are. And we can even zoom in more because we did it on a pretty big domain. Okay. Those are the first 3 modes. So the blue one is the first mode, which is essentially the first mode that comes out of the Hermite polynomials is a Gaussian. So it's a Gaussian, centered at the bottom of that well. And the other 2 modes tend to be what are called modes 3 and modes 5 in the Hermite polynomials. And what we see here is only even modes. That's because when we put in the dynamics for that initial condition, it only generated even dynamics. I'm going to show you one other simulation here, because now that we have this, you can start seeing what ends up happening here is I get back actually, in fact, those modes that I showed you are the Gauss-Hermite polynomial modes. It basically reproduces what I know were the Sturm-Liouville functions, very close to them, but it didn't produce any of the odd functions, and that's because my initial condition had no oddness in it. And again, that highlights one of the key things here, which is, this highlights something very important, which is what your POD expansion can be is going to be limited by what you sample. If you only sample even dynamics, it doesn't produce any odd modes. So your POD is limited by your sampling strategy. So it's important to recognize that. In some cases, that's not a problem, and in some cases, it may be. So let's just rerun this. Maybe since it took a while, let's just run it for less time and run the whole thing. So what we're going to do is now run this again. And what I've done here is only made one change. And now my Gaussian is centered off a little bit. So pull up my dynamics and look what happens. So first of all, you don't need to see that quite as big. I'm going to show you this. Here's what happens. It's oscillating, but it's also moving around like this in the well. Okay? So it's sloshing around and oscillating. The modes are going to be quite different. So you still want the modes that capture this oscillatory bit, but as you slide, now you're going to have some odd modes into this thing. So now we can start looking at the singular value decay, and look at this. Quite different. So first of all, if you remember last time, the first mode had 68%. Now the first mode only is at 18%. And now it looks like you have to have at least 20 modes to capture the dynamics correctly. Right? So the dimensionality depends upon the dynamics that is occurring in your system. In the case where I had this nice even dynamics, I could get away with 4 or 5 modes. Now I need about 4 or 5 times that number of modes to do the same thing, capture the same amount of variance. The modes, what do they look like? Actually, let me just plot the real part of these modes. I think it might be a little bit nicer to look at. Run the section. There they are. That's a little nicer. There are the modes. And maybe make them line with 2 because you can barely see that. Okay, there they are. So notice this. So the first blue one is the dominant mode. And that actually looks a great deal like a Gaussian. So you still have this dominant Gaussian type structure. But now the modes are asymmetric. Before the modes were symmetric. If you run this, you'll see that the modes were completely symmetric when I start in the middle. And now the modes are asymmetric. And these are your first 3 modes. You can start seeing the asymmetry is just simply coming from the fact that this thing is sloshing around in that system. Okay? So this is a nice example, and this is actually how we would construct these POD modes. In the next lecture, we're going to actually not only take these POD modes, we're going to actually build a reduced order model from them. Here, I just wanted to sample and show you how these modes are constructed. And in particular, when you look back at the case when we started evenly in the well, I actually get back these Gauss-Hermite polynomial modes, which are known to be, sort of in some sense, the correct eigenfunction expansion basis. So this POD architecture captures something important for you, which is something you already know, which is there are, in some sense, optimal basis sets. And in some cases, they match up with things like these Hermite polynomials. And as soon as you go asymmetric, now you're getting yourself a much different set of optimal modes. And so this is something we'll build on as we go forward. But by the way, for the data we have, these are, in fact, the guaranteed optimal modes. That's something that SVD does guarantee for you. But it also, you have to come into this with a little bit of caution, because you can only represent things you sampled. That's one of the fundamental things about taking snapshots of your dynamics, looking for a low dimensional embedding. It's fine as long as your dynamics doesn't live outside of that embedding.